Hi, everyone. We're going to review polar curves. As we know, there are a few graphs that are not done easily on the rectangular coordinate plane, since the rectangular coordinate plane is based on perpendicular lines and squares. So shapes like a heart or a rose or a spiral are not easily done on the rectangular coordinate plane. That's why we need the polar grid. Now, the polar grid is composed of two axes, just like we have the X and Y axes. However, instead of rectangles, instead of squares and perpendicular lines, we have concentric circles centered at what's called the pole. And as we go outward, each circle has a radius. The first circle has a radius of 1. The second circle has a radius of 2, etc. And in order to locate a point on the plane, we need an angle. And that angle is the terminal side of the angle in standard position. So I've divided the grid into partitions of pi over 12. So this is 0. This is the terminal side of pi over 12 radians, 2 pi over 12, otherwise known as pi over 6, 3 pi over 12, otherwise known as pi over 4, 4 pi over 12, which is pi over 3, 5 pi over 12, and then 6 pi over 12, which is known as pi over 2. And if we go around, we have 12 pi over 12, which is pi. And then this is 3 pi over 2, which is 18 pi over 12, etc. And the angles are always in counterclockwise motion. So we name a pair as the radius and the angle. So let's plot, say, the second one, 2 comma negative pi over 3. So negative pi over 3 is equivalent to negative 4 pi over 12. So we have to go in the clockwise direction, starting from 0, 4 down, 2, 3, 4. So this is the terminal side for 4 pi over 3, 4 pi over 12, I should say. And because the radius is 2, we locate the circle on that terminal side with a radius of 2. And the point is right here. So that's the point 2 comma negative pi over 3. Now, if the radius is negative, then we reflect that over the pole. So for instance, if we wanted to plot point to plot set with negative 1.57 pi over 6, 7 pi over 6 is really 14 pi over 12. So we have to go 2 down this way. So this is 7 pi over 6. This is the line 7 pi. Well, the angle 7 pi over 6 is really this way, but we look at the terminal side. If it were positive 1.5, the point would have been here. But because it's negative 1.5, we have to extend this terminal side to the opposite side and locate 1.5 in the opposite direction. So we reflect this point over, and that point is over here. So this red point is this pair. Okay, so an easy way to think about it is the following, which someone I read somewhere in one of the lessons. They said that if we consider taking the number line and rotating it, so if we have our number line, and this is the positive, that's the negative, and we keep rotating it around. So we could think of all of these rays coming out of the pole as the number line that's being rotated around. And so if we rotate it so that the positive side of the number line stops at angle theta, if R is positive, go to the positive side of the number line. If R is negative, we go to the negative side of the number line. So if you just imagine the number line being rotated, we could think of it that way. All right, now to convert polar points to convert polar coordinates into rectangular coordinates, we need a brief lesson of how they came about. So if we go back to the unit circle on the coordinate plane and how we define sine and cosine, we have the circle on the coordinate plane. It's really the unit circle. And we have the angle theta. Its terminal side is here. So this point has coordinates cosine theta, sine theta. But that's if we've got a unit circle. If we had any radius, then the coordinates would be r cosine theta, r sine theta, because of a dilation. So I'm going to erase this. So this would be r cosine theta, r sine theta, which are the x and y coordinates of this point, where this is x and this is y. So from that little diagram, we've got many equations coming out that we should know and that are important when we convert from one system to another. The first is x equals r cosine theta and y equals r sine theta. And these equations are the parametric forms for x and y in terms of theta. Okay, and they convert polar points into rectangular points. We also see that r is the hypotenuse of a right triangle, which is just the square root of x squared plus y squared. And the tangent of theta is simply y over x. So these four equations we should know. So for instance, if we wanted to convert the polar point to √3, which is r, and pi over 6, which is theta, we simply use this equation, x equals r cosine theta, which is 2√3 cosine pi over 6, and that gives us 2√3 times √3 over 2, which simply gives us 3. So the x coordinate on the rectangular plane is 3. To get the y coordinate, we substitute this into y equals r sine theta. That's 2√3 sine pi over 6, which is 2√3 times a half, and that gives us √3. So in the rectangular coordinate system, this point on the polar grid would name 3√3 on the rectangular grid. But they are the same point. They name the same point. But note that √3 is very difficult to find on the rectangular grid. It's an irrational y coordinate, but we can certainly approximate it. Now, when we convert rectangular points to polar points, it's a little trickier. We have to consider the quadrant in order to find the angle. So this point, this ordered pair is in quadrant 4, and this ordered pair is in quadrant 2. All right, so to get r, we simply substitute it into the square root of x squared plus y squared. So in this case, it's a square root of 3 squared plus negative 3 squared. And leaving that up to you, the answer comes out to be √18 or 3√2. So that's r here. In the other one, r is the square root of negative 4 squared plus 4√3 squared. And leaving that up to you, the answer is an even 8, and r is 8. To get the theta, we use the tangent ratio. Tan theta is equal to y over x. So that is -3 over 3, which is -1. So the reference angle here is 45 degrees, But in quadrant 4, it would be 315 degrees, which is equivalent to 7 pi over 4. So the polar point for 3, -3 would be 3 root 2 for the radius and 7 pi over 4 for theta. But that we could also write that as 3 root 2 and negative pi over 4 if we go in the clockwise direction. All right, and in B, we have tan theta is equal to 4 root 3 over -4, which is negative root 3. The reference angle here, I believe is, oh no, the reference angle here, I believe is 60 degrees. So in quadrant 2, that would be 120 degrees, which is 2 pi over 3. So the polar point would be 8 for the radius and 2 pi over 3 for the angle. So for coordinate conversions, we have to remember that x equals r cos theta and y equals r sine theta. And we will be using this a lot when we want to get the derivative on the derivative of a polar curve. Okay, and again, we use this to convert polar into rectangular. But to convert rectangular to polar, first we have to consider the quadrant. To find theta. And then the radius is simply the square root of x squared plus y squared. That's very easy. And tangent of theta is equal to y over x. Or you could just say theta is equal to arctan y over x. All right. So let's use these ideas to do a little bit of conversion of equations. All right, so I've got 3 equations here. The first is a horizontal line, which is graphed here, and also on the polar grid. The next is another line, which is also graphed on the polar grid. And the third is a parabola, which is also graphed on the polar grid. But their equations are different. And to find the rectangle from rectangular to polar, we simply use the substitution. X equals r cosine theta and y equals r sine theta. We substitute and solve for r. So r will be a function of theta. So in the first problem, if y equals 6, then we'll just say r sine theta is equal to 6. Divide each side by sine theta, and this is our polar curve. R is equal to 6 secant theta. And as you can see, that's the graph we have, the same graph. All right, in the next one, we substitute x and y, and we're going to add 1 on the other side. So we get 4r cos theta minus 2r sine theta. Factor out an r. We don't need to factor out the 2 because our goal is to get r by itself. So we get r is equal to 1 over 4 cosine theta minus 2 sine theta. And there's the graph here, except the equation was cut off a little bit. Okay, and the last one was a parabola. So again, we write r sine theta for the y is equal to 4 times r cosine theta squared for the x. So we have r sine theta is equal to 4r squared cosine squared theta. And we could divide each side by r since r cannot be 0. And we end up with sine theta is equal to 4r cosine squared theta. So r is simply sine theta over 4 cosine squared theta, not a trivial equation at all for a parabola on the polar curve. Okay, now to change polar to rectangular, we have to use a little bit of creativity and fit these two equations and find them within the formula. So if we rewrite cosecant as -1 over, well, 1 over sine theta and cross multiply, our sine theta is already y. And this is our horizontal line that we have pictured in both. And in the next one, if we do cross multiplication, r sine theta plus 3r cosine theta is equal to 2. Well, r sine theta is our y, and r cosine theta is our x. And that is the graph of the line that we have here. Okay, so that's basically it. Notice how important these two have become. Now we should know our polar graphs. The basic polar graph, to graph r equals 2, those are all the points along the circle with a radius of 2. So it's just this graph. Note that on the rectangular coordinate plane, we would have to substitute the square root of x squared plus y squared for r, and we would get the equation of our circle centered at the origin. Okay, but notice how simple graphing curves are on the polar grid. Okay, theta equals pi over 3 is exactly what we think it is. It's just the ray for pi over 3, and pi over 3 is equivalent to 4 pi over 12. So we have to count up 4. 1, 2, 3, 4. So this is pi over 3, but we also include this piece. So this entire line is theta equals pi over 3. All right. And then with something that's not just r or theta, but something like r equals secant theta, well, in that case, we could rewrite this as 1 over cosine theta, and we get r cosine theta equals 1. We know this is x. So on the rectangular coordinate plane, that's the vertical line x equals 1, which is somewhere around here. Okay, so sometimes it is easier to convert to rectangular coordinates. All right, now let's take a look at more complicated curves. Whenever we have a curve in the form of a cosine n theta, the n, well, this represents a rose. And if n is odd, we have n petals for the rose. And when n is even, we've got 2 n petals. We double the number of petals. And what's interesting here, and the reason why I picked this particular one, is that the complete rose is graphed from 0 to pi. And when we go around again from pi to 2 pi, we go over the rose again. So that we will need to remember when we get to area of roses, or getting the area of one petal of the rose. So let's go through it. I made a chart of theta, the angles, in intervals of pi over 12, and we substituted into our equation 3 cosine 3 theta and computed it and approximated it. So the rose begins like this. The tip of the petal is the absolute value of the coefficient. So it starts at 0.3. So it starts here. And then it goes pi over 12, 2.1. So it's around here. And then it goes pi over 6 to 0. So it goes down over here. So the petal goes this way. And then it continues to, okay, it continues to the next tip, which would be, okay, here, and goes around this way. So this is from the first cycle. So I guess this would be from the, let's say, well, if it's from 0 to pi, then we subdivide it into 3 subintervals. So it would be like the first 60 degrees. All right, and then for the next 60 degrees, it goes around this way. This is 2. This way. And then it goes up to this tip. 1, 2, 3 here. Oops, didn't mean to make it a straight line. That's 2. And then the last cycle, the last 60 degrees, it closes the rows. It closes it here and goes around this way. And that's 3. So, and again, the full rows is graphed in the interval from theta equals 0 to theta equals pi. And then from pi to 2 pi, we outline the same thing again, 1, 2, 3. So let's just quickly see that on Desmos. So I'm going to see if I could share this with you. Let me see if I could just get out of this, go to this. Okay, so here is my rows, and I don't know if I could write on this. And I'm going from 0 to A, where A is from 0 to 2 pi. So I'm going to move this, and notice that that's the first cycle. The second cycle, the last one. And it's complete when A is 3.14159, which is pi. And then it goes over it one more time, but we can't see it here, from pi to 2 pi. So that's the rows. And you could have a lot of fun on Desmos to look at the graphs. All right, so that's my demo. Now let's go back. Okay. All right, now other polar curves we should be, well, we just did this. Rose curves. And remember, if we go back to this rose, cosine, any polar equation with cosine is symmetric with respect to the x-axis. And anything with sine is symmetric with respect to the y-axis. Okay, so this rose, if we fold it along the x-axis, it would overlap itself. All right, so since we're on roses, this is our 3 rose petal that we just did. And this would be our 4 petaled rose where, well, how many do we have here? N is 4. So if N is 4, then we have 8 petals, I believe. 1, 2, 3, 4, 5, 6, 7, 8. So if N is 4, we have 8 petals, and it would look like this. For sine, well, this is when N is 5, and that's symmetric with the y-axis. And when N is 2, we have a 4-petaled rose. And we could see that sine is symmetric with respect to the y-axis. All right, and that's basically the rose. That's a very popular question on the AP. The other curve we should know is a cardioid. And a cardioid is an equation of, in this form, A plus or minus B cos theta, or A plus or minus B sine theta. The symmetry is the same, right? But when A equals B, we have what's called a cardioid. And this cardioid is a cosine cardioid because it's symmetric with respect to the x-axis. If A over B is less than 1, that is to say A is less than B, we have a cardioid with an inner loop. okay? And that we would find by finding the radii of various angles. And if A over B is between 1 and 2, we have a limacon with a dimple. And of course, we've got various limacons. Limacon stands for lima bean. And again, usually most polar curves need the interval from 0 to 2 pi to get the full sketch. But that particular rose curve was the exception. All right, and then we've got other circles, a number cosine theta, a number sine theta, again, symmetry with respect to the x-axis and y-axis. And depending on what A is, if A is positive, then we have it to the right or above. If A is negative, it would be to the left or below. And then, of course, we've got lemniscates in this form, but I find that circles, roses, and limacons, cardioids, are the most popular. All right, okay, before we go on, I'd like to now convert polar curves into rectangular form. I'm sorry, not that. Polar curves into parametric form, all right? Now, the parametric equations are these two. This is the parametric form for the rectangular coordinate plane in terms of theta and r. So if r equals 4, we simply substitute x equals 4 cosine theta and y equals 4 sine theta. And those are the parametric equations. And we will need that when we get to the derivative. So we have to practice this. The parameter is theta, just like the t. Okay. In the other one, if r equals 4 sine theta, well, if x equals r cos theta, we would have x equals 4 sine theta cos theta. And if y equals r sine theta, we would have y equals 4 sine theta times sine theta, or 4 sine squared theta. Okay, so notice that the r is incorporated. Okay. All right, now the same is true in the next one. X equals r cos theta, y equals r sine theta. And remember, C comes before S in the alphabet, so X comes before Y. That's how I remember it. So I get X equals 4 over cosine theta times cosine theta, which is just 4, and Y equals 4 over cosine theta times sine theta. Okay, and of course we could simplify that. But when we get to something, now this is a cardioid. Not that we have to know that, but the A and B are equal to each other, right? It's nice to know. So X equals R cos theta, Y equals R sine theta. So substituting, we get 1 plus sine theta times cosine theta, and this becomes 1 plus sine theta times sine theta. All right, and we would stop here usually, but in the next question, we're going to end up getting the derivatives with respect to theta, and it's worth simplifying them, especially we want to avoid the product rule. We want to stick to a simple chain rule. So if we distribute here, we get x equals cosine theta plus sine theta cosine theta. And here we get sine theta plus sine squared theta. All right, now recall that there's a double angle formula, sine 2 theta equals 2 sine theta cosine theta. Well, I certainly don't want to use a product rule here. I mean, I could, but I want to avoid that. So this can be rewritten as 1/2 sine 2 theta is equal to sine theta cosine theta. So x here is cosine theta plus 1/2 sine 2 theta, and I'll need it below. And this I will leave because I don't need a product rule. I just need a chain rule to differentiate it. So going below, since we know that y is equal to sine theta plus sine squared theta, to differentiate this with respect to theta, we get cosine theta plus 2 sine theta cosine, 2 sine theta cosine theta. I should put it in order because it's 2 sine theta to the first power times cosine theta, the generalized power rule. And of course, I could write sine 2 theta for that, but I'm not going to bother right now. Oh, well, actually, let's do it. This is cosine theta plus sine 2 theta. Okay. And well, since x is equal to, what was x? Cosine theta plus 1/2 sine 2 theta, then dx d theta would be negative sine theta plus 1/2. Now this is the chain rule. The outer function is sine, so that's cosine 2 theta, and the derivative of the inner function is 2. So dx d theta is simply negative sine theta plus cosine 2 theta. So to get the slope on the rectangular coordinate plane, we use the parametric form of the derivative, but in terms of theta. And that would be dy d theta over dx d theta, which is equal to, okay, well, I have cosine theta plus sine 2 theta, oops, and negative sine theta plus cosine 2 theta. And I would do this step by step. First, I'd get my x and y in parametric form. Then I would get my dy d theta and dx d theta and use identities. Well, actually use identities when you get the x and y, and then differentiate, divide, and substitute if we need the slope. So to get the slope of the tangent line, we're going to put pi over 3 into this. And believe it or not, we're really finding what the slope would be on the rectangular coordinate plane. It's really strange. We're doing a lot of conversions. So we substitute this in here, and we get cosine pi over 3 plus sine 2 pi over 3 divided by negative sine pi over 3 plus cosine 2 pi over 3. And very quickly, that gives us 1/2 plus root 3 over 2 divided by negative root 3 over 2 minus 1/2. And if we factor out the negative 1 in the denominator, I think you'll see that this fraction is negative 1. And that's the slope of the tangent line. Okay, and then once in a while, they're very unexpected. They might have us solve a trig equation. So to find out where the tangent line is vertical or horizontal, in this case, when the tangent line is vertical, a vertical tangent line has an infinite slope, which implies that the derivative, the denominator of the derivative must equal 0. So it's important to know that the denominator is dx d theta. That has to equal 0, but the numerator cannot equal 0. So we always have to check that. And that's a little more work with polars. So let's go through it. So the dx d theta is negative sine theta plus cosine 2 theta, and we make that equal to 0. And we have to end up with a quadratic equation. And the identity for cosine 2 theta in terms of sine is 1 minus 2 sine squared theta equals 0. And if we divide everything by -1, we get 2 sine squared theta plus sine theta minus 1 equals 0. This is factorable to 2 sine theta minus 1 to sine theta plus 1 equals 0. We set each factor to 0. We really should show that step. And we get sine theta is 1/2, or sine theta is -1. Now, the angle that has a sine value of 1/2 is 30 and 150. So that is pi over 6 and 5 pi over 6. And the angle whose sine is -1 is 270. That's 3 pi over 2. But when we substitute this into dy d theta, it does equal 0. So we reject this, right? We reject it. So here are the angles at which this cardioid has a vertical tangent. So pi over 6 is here. This is theta equals pi over 6. Well, part of the line anyway. And 5 pi over 6 is here. Wait, I'm just trying to make sure I'm looking at this correctly. The points are here on the cardioid. And notice that at those points, we have 2 vertical tangents. So we're okay. But to get those points, theta is not enough. We've got to get the radius. So to find r, we substitute back into the original cardioid. And the original cardioid was 1 plus sine theta. So when we substitute sine of pi over 6 or 1 plus sine 5 pi over 6, they're both 1/2. So we have a value of 3/2. So the points at which we have a vertical tangent are the polar points, are 3/2 pi over 6 and 3/2 5 pi over 6. And that is the idea. So it's a little bit more involved. Okay, now we don't really need the summary because the steps are there. First, convert your polar equation into parametric form. And notice that r is a function of theta and it's actually substituted in here. That's what we did. And then we differentiated each with respect to theta and divided. But if we wanted a formula, which I don't expect you to use, I'd like you to do it step by step. We have dy d theta over dx d theta. And to get these, we need the product rule because f of theta is a function of theta and cosine times cosine theta and f of theta times sine theta. So very quickly, I'm going to write this out for you with the product rule. So these are the parametric forms. Find dy d theta, dx d theta, and divide. Dx d theta and divide. And of course, if using trig identities, it helps. But the formula is the derivative of f times sine theta plus cosine theta times f of theta. And the other one is a derivative of f of theta cos theta minus sine theta f of theta. And again, this is very important. To find horizontal tangents, we set the numerator of the derivative to 0, but the denominator of the derivative cannot equal 0. And for vertical tangents, the denominator has to equal 0, but the numerator must not. So that's why I did that particular problem beforehand. All right, then we've got multiple choice. I don't think they would ask you number 9 on the AP because that's more like a pre-calc question. But A is 2 and B is 4. And because A is less than B, this is a limousin with an inner loop. Okay, if we look at 10, we simply substitute x equals r cos theta and y equals r sine theta. So we get x equals 5 theta cos theta and y equals 5 theta sine theta. And that is choice A. 11 involves work and it requires the steps we talked about. So let's do it. First, we're going to write it in parametric form. So what is r? R is 1 plus cos theta times cos theta. And this is 1 plus cos theta times sine theta. Now we distribute. I get cosine theta plus cosine squared theta. And here we distribute and I get sine theta plus cos theta sine theta, which we said could be simplified into sine theta plus 1/2 sine 2 theta. Okay, notice how we pick up these techniques. So dx d theta here would be negative sine theta plus 2 cos theta negative sine theta. And dy d theta would be cos theta plus 1/2 cos 2 theta times 2. All right, cleaning this up a little bit, we get negative sine theta minus 2 sine theta cos theta. And this one is cos theta plus cosine 2 theta. So this looks okay. All right, we could rewrite this one as negative sine theta minus sine 2 theta. Okay, that's the best we could do. So dy dx is dy d theta over dx d theta, but at theta equals pi over 6, we're going to put pi over 6 into everything. So let's see if we could do that. We get cosine pi over 6 plus cosine 2 pi over 6, all divided by negative sine pi over 6 minus sine 2 pi over 6. So this gives us root 3 over 2 plus 1/2 divided by negative 1/2 minus root 3 over 2. This is really similar to what we just did beforehand. And the answer is -1. Okay, let's now look at this AP question. All right, we will not be able to do A. We'll do that in our next lesson because we don't know area, but we certainly can do B and C. Okay, so this is a curve, R equals 1 minus 2 cos theta, and it looks like 1/2 of a limousin with an inner loop, right? Because notice it's graphed in the interval from 0 to pi. And if you plug in 0, well, cosine 0 is 2. I mean, cosine 0 is 1. So we get 1 minus 2, which is -1. And notice how we get this point here. Okay, but be that as it may, it looks like they graphed it in the rectangular coordinate system, but imagine the rectangular coordinate system overlapped with the polar system, and we would get that curve. All right, so anyway, they say to write expressions for dx d theta and dy d theta. So this is just like the problem we did. So let's do it. X equals r cos theta, y equals r sine theta, x equals r, 1 minus 2 cos theta, cos times cos theta, y equals r, which is 1 minus 2 cos theta sine theta. We're going to get the same trig identities as long as we have like limacons and cardioids or limacons with inner loops. So we get cosine theta minus 2 cosine squared theta, which is good. Y is equal to sine theta minus 2 cos theta sine theta, which can be written as sine theta minus sine 2 theta. Okay, so dx d theta, and this is the answer they want, is negative sine theta minus 2, oh, excuse me, should be minus 4, because we're going to multiply the 2 there by the exponent 2. So it's minus 4 cosine theta to the first, and the derivative cosine is negative sine theta. So cleaning this up, we get negative sine theta plus 4 cosine theta sine theta. I could use a trig identity here, but I'm not going to worry about it because I don't have to differentiate it. Thank goodness. Okay, and the derivative here would be cosine theta minus cosine 2 theta times 2. I'll put that in the front. So the answers to the problem, they didn't ask for dy d theta, dy dx. They only asked for dx d theta and dy d theta, and that's all we write. That's all that we give them. But we're going to probably use this in the other part. So let's look at part C. In part C, they say, write an equation in terms of x and y for the line tangent to the graph of the polar curve at the point when theta is pi over 2. So again, dy dx at when theta equals pi over 2 is equal to dy d theta at theta equals pi over 2 divided by dx d theta when theta equals pi over 2. So substituting accordingly, we get cosine pi over 2 minus minus 2 cosine 2 times pi over 2. And the other one would be negative sine pi over 2 plus 4 cosine pi over 2 sine pi over 2. Okay. Well, anyway, cosine pi over 2 is 0. And cosine of pi is negative 1. And sine of pi over 2 is negative 1, but we put the negative there. And the other part will be just 0. So the answer is negative 2. That's the slope of the tangent line. But to get the equation of the tangent line in terms of x and y, we need to get the x and y coordinates on the rectangular coordinate plane. And the only way to do that, as we did before, is to substitute pi over 2 into the equation. So if r is equal to, what is it again? 1 minus 2 cos theta, right? And we know that x is equal to cosine theta minus 2 cosine squared theta. This is where the pi over 2 will go to get x. So that's cosine pi over 2 minus 2 cosine squared pi over 2. And that would give us an answer of 0. That's the x coordinate. The y coordinate is sine theta minus sine 2 theta. This comes from the parametric form of the polar curves. So we get y equals sine pi over 2 minus sine of 2 times pi over 2. And the y coordinate would just be 1. So the equation of the tangent line, the point of tangency 0, 1. So the equation of the tangent line would be y minus 1 is equal to negative 2 times x minus 0. Okay, and that's it. Now, there's another question I'd like to add here that I thought was really nice. And that question, and I picked it up from another AP. Oh, here it is. What is the average distance from the origin to the point on the polar curve r equals 1 minus 2 cos theta on this interval from 0 to pi? Okay. Now, when I saw average distance, I was thinking of arc length, but we don't know the arc length of polar curves. We didn't do that. We only know the arc length of parametric curves and the arc length of a curve on the rectangular plane, but not polar curves. We didn't do that. So what they're talking about is the distance from the origin. So if this is the origin, and this is a point on the polar curve, the distance between the origin and a point on the polar curve is this line segment. Or maybe it's this line segment. These are the terminal sides of the angles, right? But of course, the angles go on forever. What makes it very unique is the radius. What radius do we pick on the terminal side of that angle to plot the curve? So this is really asking us, what is the average radius? Radius, because the radius is really the distance from the origin to a point on the polar curve. All of that is another name for the radius, right? So what is the average radius of this limaçon on the interval from 0 to pi? So this is really asking for average value of a function. So the average value of a function on an interval is 1 over b minus a times the definite integral from a to b of the function. So in the polar world, the average radius would be 1 over pi minus 0, the integral from 0 to pi of f of theta, which is r, because f of theta d theta is really what r is. So r is 1 minus 2 cos theta d theta. And this is not bad to integrate. We don't need u sub. The integral is theta minus 2 sine theta from 0 to pi. So we could factor out the 1 over pi, and we get pi minus 2 sine pi minus 0 minus 2 sine 0. Okay, this is 0. This is 0. So the answer is 1 over pi times pi, which is just 1. Okay, we covered a lot in this one lesson, but I am very concerned about the calculus. So review polar curves, and we'll continue this next time. And I wish you all a very, very wonderful day. See you next time. Bye.